Okay, thank you very much. So this talk is about optimization with inexact gradient and function. So my co-authors are people from Toulouse. So Toulouse is south of France. So Ewan Simon is from Toulouse. David is from Canada, and Philippe Touin is from University of Namur in Belgium. So this work is supported by ANITI, which is a Center for Artificial Intelligence in Toulouse. So I'm going to talk about optimization problems where you are going to consider inexact function gradients. First, I will describe why it is important, why this problem is very important. I will take a very simple case to start with, which is a quadratic case. So that is related to least squares, for instance. And then I will propose some ideas to go beyond the least squares framework and address the smooth and non-convex optimization. So why multi-precision? First, and here I'm just paraphrasing Nick Hayam from University of Manchester. If you do computation, so first, variable precision is more and more accessible on computers. So it's very easy if you run in MATLAB, for instance, just type single of a vector. Yes?
I don't know what variable precision.
Okay, yes, thank you for the question. So if you do standard computation in Fortran or C, you work with numbers that are stored in 64 bits. And in most systems, you can also play with numbers that require less digits for their representation. You can have 32 digits, and in some systems, you can have even 16. And in embedded systems, you can have even less digits. So the idea is, can we compute with reduced number of bits? So this is the answer to the question. So single precision here would be 32 bits instead of 64, and you see that you gain a lot. You gain a factor of 14 if you work in single precision. So the challenge here is to understand what you can expect from algorithm if you run them with such a reduced precision, or even more importantly, as a mathematician, we'd like to know whether it's possible to design algorithms that could work with such a multi-precision arithmetic. That is, we would like to have algorithm with probable convergence results. For instance, we are interested in getting a point where the gradient is zero of a nonlinear function. Is it possible to do that even with reduced arithmetic? How to manage this reduced arithmetic? So this is the main question: is how does multi-precision arithmetic affect the convergence rate of algorithm and also final accuracy of minimization algorithm? As I said, I will start with the very easy case, simple problem of quadratic optimization. And you will see that we can have some surprise here while playing with inexact computation. So why is this one? I mentioned that it is related to least squares, and also least squares is a fundamental tool for data analysis. It is also a very simple case for nonlinear optimization. So if you cannot do multi-precision computation with this one, maybe you cannot work on more difficult problems. And also it is a building block for more general optimizer. And more generally, when you solve PDEs, you are quite often led to solve this kind of quadratic problem when your problem is elliptic, for instance. Okay. So I'm going to consider here a particular solver, which is a projection method. So it's a conjugate gradient method. It has many equivalents methods like full orthogonalization method. So I will tell a bit more about the conjugate gradient method. Why? Because in the quadratic case, if you do something like the steepest descent method, which would be closer to first order method, The convergence rate of the method is 1 minus 1 divided by condition number of the matrix. Whereas if you work with conjugate gradient, you have 1 minus 1 of the square root of the condition number. So conjugate gradient method is a much faster algorithm. Probably you can prove this kind of convergence rate, especially if the matrix at hand is very ill-conditioned. So this is why I'm interested in this problem. So conjugate gradient and form, I will present those two algorithms as, in fact, inexact arithmetic. So if you do all your computations on the paper, they give the same result, and we will see what happens when you do reduced computation. And in all these methods, so what we assume that what dominates the cost is the computation of the matrix vector product with the matrix of the quadratic form, which amounts to say that the gradient is the most expensive part. So you will see that there is also some linear algebra in the conjugate gradient method, but here I assume that A is such that this dominates the cost. So it means that this is the quantity I would like to perform in reduced arithmetic to save something. The particular point of view I will take is that I will focus on the decrease of the quadratic form I can get with my iterative method. So I will not be interested in the 2 norm of the residual, for instance, of something like this, because so it is important if you do optimization, because you want to control, if you do a quadratic approximation of the method, you want to control the decrease of the quadratic method. But maybe more importantly here, if the least squares problem is often associated with a Gaussian method, a Gaussian model, and then you are trying to maximize the likelihood. And what matters is whether you manage to improve your likelihood with your method. And this is really given by the by the value of the quadratic function. So in other words, the stopping criteria I will use for my method. So I said that I would like to design algorithms that would perform well, even if the arithmetic is reduced. So I want to design algorithms that would meet the same stopping criterion, this one. So the idea would be, I want to have a decrease compared to the optimal value of my quadratic, which I don't know, of course. So I want to design an algorithm such that this quantity can be driven below epsilon times this quantity. So this is the initial quantity. And I want to prove that my method can do that. Is it okay? So another application where I have the same issue of solving here a quadratic problem, and I want to play with various level of accuracy, is the framework of data assimilation. So I will talk more about this framework tomorrow. But just in a few words, in data assimilation, in the most basic method, which is a variational method, you have to minimize sequentially this kind of nonlinear function. It is nonlinear because the operators here are nonlinear. This is the dynamics of your system. This is an observation operator. And what is very important here in this method is that all this quantity, they live in very high dimension. So typically, X belongs to R to 10 to the 9. So it's really a very large scale problem. And you want a solution which is as accurate as possible. Because here, it's not, you don't want to know whether it's a cat or a dog, but you really want to have several digits in the temperature, for instance, you forecast in this kind of application. And in this case, if you consider this problem, a typical method to solve this would be to linearize all your operators in the norms here. And then you have a quadratic problem to solve, this one. And if you stack all the matrices into a long matrix for H, for M, and for R, and for Q, to have a simpler notation, the problem takes this from here. So it's a particular sum of square problem. And to solve this, I can run my favorite method, like the.
So you do that at each step. You do that.
Yes. So it's we do some time windowing, and for each window we solve this problem to prepare a condition for the next window. Yes. So the problem is very large, as I said, typically 10 to the 9 for the space where you look for 1x. And this is the Hessian, so this is the matrix of my quadratic. And you see that this matrix is kind of nasty because you have already an inverse that appears in the matrix itself. The problem is that you don't have, so even if D minus 1 is itself an inverse, it's a block diagonal matrix that you want to inverse. The problem is that all these matrices are very hard to invert. So this means that you would like to run an iterative method where at each time your matrix vector product involves itself the inversion of a matrix, and you have to decide how precisely you have to solve all this linear system in your iterative method. Okay. Another reason for focusing on this problem is this issue about energy dissipation during the computation. So this is for people who are working with computer architecture. This is considered as the next barrier that will be important in computer design. It's energy dissipation. And energy dissipation is proportional to the square of the number of digits that are involved in the computation. So this is what you can read in this literature. And this is why it is again appealing to do as much as possible computation with a reduced number of digits.
So careful about energy dissipation. They are conscious about the climate. They are. It's a matter of cost, or is it simply that
it's
so much that
it's a cost to cool down the system. This is very expensive. Yeah. So and in nowadays computers, you have GPUs typically where you can play with 64 bit of accuracy, but you have CPUs. Here, so this is a 64, 32, 16. You have GPUs where you have 32 bits of accuracy. So already people in machine learning, they are working with multi-precision arithmetic. I don't know if they realize, but it's already a matter of fact that they do that. Okay. So conjugate gradient method and form, the full orthogonal method, the two methods I mentioned, are two methods that are called Krylov method. So maybe I'm going to explain in one line what is a Krylov method. So Krylov method is you want to design, so you want to minimize a quadratic function, this one, okay? And you would like to have a method, an iterative method, that will give approximation for the solution to that problem. And one way to find such an approximation is instead of minimizing this over Rn, you minimize over a subspace of Rn. So it can be, for instance, the linear space which is spanned by B, AB, A to the power k minus 1b. So this would be, you can, in fact, all these methods, conjugate gradient and form, are methods that compute this step. They compute this, sorry, x, it belongs to this, and this is xk. You compute this. And it turns out that you can do this very efficiently. This goes back to the paper by Hastings and Stiefel in the 50s. You can do this very efficiently, and at each step of this algorithm, you perform an incremental minimization. Each time you go from step k to step k plus 1, you add one vector in the Krylov subspace, and you have updating rules to update the solution to this problem. Okay, and I will give you exactly the code for conjugate gradient method. Okay. So I will consider also the two cases which I mentioned in the introduction. The first is when you have discrete accuracy levels, 64-bit, 32, 16, and so on, and continuous. So when, for instance, your matrix vector product involve a matrix inversion, you can decide in a continuous manner what will be the accuracy of the solution of your linear system. So these are two possibilities. So a first remark, I'm interested in this quantity, which is a decrease of the quadratic. With very simple algebra, you know that you realize that this quantity is in fact nothing but the residual of your linear system, of the gradient of your quadratic, but in a norm which is the inverse of the norm of the quadratic. So it's a dual norm of the, with respect to the canonical product, it's a dual norm of the norm which is induced by the quadratic. Okay, so just this. So it means that we can monitor our decrease in the quadratic just by monitoring the value of this residual along the iterations. So we work with the A-1 norm of the gradient.
I'm sorry, are you working in a finite region of Rn, or are you working with a positive A, or what?
You mean for
the minimum is negative infinity?
Yes. So here A is symmetric and positive definite. And positive definite. This is why we induce a norm and we can take the dual norm. Thank you. Okay, so I want to measure the accuracy on my matrix vector product. And a convenient way to do that is to consider, to model the error in the matrix vector product by a perturbation of the matrix instead of the perturbation of the vector. So if I compute a matrix vector product, I will model my inaccuracy with this term here. So this is common, this is called backward error analysis or something like this. So first thing is, as you already mentioned, it's very important to keep in mind that we are working with a system which is symmetric and positive definite. And I will consider perturbations that will maintain this property of the matrix I will encounter during the computations. And again, if I take an appropriate norm for measuring the error, which is performed here, and this appropriate norm is natural, on the input space of my matrix I take A, and on the image space I take A-1, and this is a natural norm induced. And so if this norm is below 1, less than 1, you maintain the property. So it means that this norm performs a scaling of your matrix. Typically, with the two norms, we would have here the smallest singular value of A that will play a role. But here, with this particular norm, that's the case. So a key remark now is I want this quantity to be driven below some quantity. This quantity is the same as the square of the residual. So the question is how to monitor the square of the residual of my iterates, and how can I make sure that this one will go to 0. So a remark is that if for any vector Rk, if this holds, so if the gap between these two vectors and this vector are both less than this quantity here, then just by triangular inequality, my residual in x, so I write R of x equal to this plus this, and then just since these two quantities are below this, I use the triangular inequality, and I get directly that this one is below epsilon q of x star. So I get my, my stopping criterion satisfied, provided that my gap with a vector, which can be anything, but provided that my gap with a vector is less than this and the norm of the vector itself is less than this, then at this point of my iterations, I get satisfaction of my stopping criterion. And now I will take a particular vector and apply this. This would be the key point. Okay, so I will start probably with conjugate gradient because it is a more familiar algorithm. So conjugate gradient just does this. And if you do some linear algebra, you can prove that when you add a vector to this, you have just to make one iteration of this K loop. So it's very simple, as you see, just one matrix vector product, and then it's basic linear algebra, multiplication with scalar, and so on. So what is standard conjugate gradient is just here ck equal a pk. And my conjugate gradient, the one I'm interested in, is the one with the perturbation. And my question is how to manage, even with reduced arithmetic computation or with some EK here, how do I manage to meet my stopping criterion with
anything as long as the norm is smaller than
exactly. For the moment, it is the only constraint. Okay, and here I have plenty of vectors. In the previous slide, I said I can take any vector here, and here I will take a vector which is available in the algorithm, is this vector Rk. So what is Rk? Here it is the estimation of the residual in my iterative method. If there was no perturbations, Rk would be the residual of the system. But since here I am perturbing my matrix vector product, this Rk is not anymore the residual of my linear system. However, I will take this quantity in my equality in my criterion here. Okay. So now the question is the following: with this particular Rk that occurs in the conjugate gradient algorithm, can I choose a perturbation E such that the gap between this Rk, which is not anymore the residual of my linear system, and the true residual of my linear system. So can I choose an Ek such as this quantity is bounded by some number a priori? And then, is it true, or can I observe that in practice, my Rk, this quantity, will go below this? And if this is the case, if I can monitor the gap and observe that this quantity falls below this threshold, I can guarantee that I've met my stopping criterion. Okay. So, and this is what happened with conjugate gradient. You can prove. So it's how do you do that? You write the original algorithm, perturb the algorithm, and then you do the difference line by line of the algorithm, and you bound. And by doing that, you observe that if the norm in your matrix vector product, if it is below this quantity, and this quantity are all quantities that have been computing before in the recurrence. So there is no forward reference to a quantity that would be obtained later. So if Ej is below this quantity, then at each iteration, the gap is bounded. So I don't show you here the technical details of the proof. So you see that now what occurs, what are the quantities that are important is BA-1, so, okay, PA, so you have norm, what we call energy norm, so the norm A of some vectors, and the norm A-1 of other vectors. So if you choose perturbations that satisfy that, then the gap between this Rk, which is recurred by the algorithm, and your true residual will be bounded. And then, provided that at some iteration, the RK is below a given quantity, you can prove that you've met the stopping criterion. And from...
So here this phi, you choose it.
You can choose anything. And it's a way to balance your effort. You may want to perturb a bit more at the beginning, a bit less, and it's a way to choose that. Or if you do, for instance, the discrete perturbation where you have 64, 32, and so on. So it may be that the perturbation that you can do with your reduced algorithm, arithmetic will be much lower than what you should do. So it means that you have some budget for further perturbing later iterations. So you can, in this way, play with your effort.
So it's a control.
It's a control. Yes, you can play with that. FOM, what is FOM? FOM looks pretty similar. You see that you have, again, the dominant operation for us would be the matrix vector product here. And FOM is a method which is derived from another method which is called GMRS, Generalized Minimum Residual Method. And in this method, you take your matrix and you find a matrix with orthogonal columns such that AVK equal VKH plus some here, a rank 1 correction. So this is the case vector of the canonical basis. This is the square and upper Essenberg matrix. So you describe your matrix in a subspace VK, which is, again, just an orthogonal basis of your quadratic subspace. And then to minimize this quadratic, you solve just a linear system involving matrix HK. So if you take into account that your matrix is symmetric and positive definite, here your matrix will be tri-diagonal. And this method FOM, so either you write the algorithm, the CG conjugate gradient algorithm as I showed, or this one, you get exactly the same iterates that can be described mathematically as minimizing the quadratic function on a quadratic subspace. It's a kind of Ritz-Galerkin approach for the quadratic, where the particular subspace will be a quadratic subspace. Okay, and in this situation, you can also prove that you can bound the gap provided that the norm measured in appropriate norms is less than something. And what is interesting is that the algorithms are very different if you look at them, and also so are very different the bounds that we find for EK. They don't involve at all the same quantity. So there are questions. Is one better than the other? And also, what kind of perturbation do we get with this kind of algorithm? So we can now show some results for that. So here you have exact methods, conjugate gradients, and FOM. This is the two methods I presented. And you have the inexact methods, EI-FOM, and there is here a conjugate gradient method with reorthogonalization. What is that? So if you look at conjugate gradient algorithms, this very simple algorithm, the simplicity comes from the fact that matrix A is symmetric and positive definite. This is why you can have this very simple incremental formulation of your algorithm. And in fact, vectors here on the paper, in exact arithmetic, they satisfy some conjugacy relations. For instance, the RK, they are orthogonal if there is, of course, no perturbations. The directions, PK, they are conjugate with respect to the matrix inner product. So there are some relations. And due to finite computations, finite precision arithmetic, you lose already, even if you do the 64 computations, the standard computation with your, in your favorite language, you lose this orthogonality due to rounding errors. So people are running this algorithm, and they perform reorthogonizations, an orthogonalization that would not be needed on the paper, but that helps the convergence of the algorithm. Okay, so this is CG with orthogonalization. And I can also make this inexact. So CG with orthogonalization and CG and FOM on the paper, they are exactly the same mathematically speaking. And what we observe between those three algorithms, if we run them on a computer, is really the effect of the rounding errors in the algorithm. And it is really severe for CG. And there have been many papers on this, on understanding numerically, or there are even some results that can be proved in this context. Okay, so I'm going to compare algorithms. So for doing that, I need to measure how much I gain if I do my matrix vector product with a reduced arithmetic. For instance, I go from 64 to 32. By how much do I reduce the computational cost of my operation? And for this, you can measure it if you can implement those algorithms, you can measure it directly on your computer. But in our case, we model this by assuming that the cost is the cost of the evaluation of a matrix vector product with A is proportional to this kind of term, where epsilon is the accuracy that you require on E. Okay, so this corresponds to a process that would be linearly convergent for computing the matrix vector product. This is just that. Okay, so then we make experiments with random matrices, also with real matrices, and we use several here accuracy levels. This is what we obtain. So here you have 3 algorithms, okay, and so the dark blue here is the gap, the quantity I'm controlling along the iterations. Here I plot the negative log of the quantity. So so this is why here it's 10 to minus 6, for instance, for this particular quantity here. So what we see is if you take 10 to minus 3 here, so this line corresponds to 10 to minus 3, you see that the gap is always below my value epsilon, which is what my theory predicts. Of course, I choose E in such a way that my gap is controlled. So I just observed that, okay, it works. And then I consider...
Sorry, I don't get it. You have an E, because you didn't put I for... Is this for the inexact thing?
Yeah. So here I'm running the inexact, and in the inexact I have the RK, and I have also I can just for testing I can compute the true residual, which is the one I don't have access to in general. And if I compute this, I get those bars, and okay. Concerning the gap, everything is okay. And now I can consider also, sorry, this is the gap. This guy is the gap. And this guy here, it is just
10 to the minus 30.
Yes, so I will comment on that. Okay, so this is the gap. In green, I plotted the value of my stopping criterion. So here it means that I managed to reach my stopping criterion within the computations. And the yellow, it's a quantity which I did not present because it's a bit, the formula are a bit heavy, but they are presented in our paper. I need to compute in various places of the algorithm, and to stop the algorithm, I need to know what is the value of my quadratic. So what is the norm of my quadratic is the value of my quadratic, sorry, it's this quantity here. And of course, since I don't have access to A, I need to approximate also the value of the quadratic. And here, this is the error of the value of my quadratic. So this means that I'm satisfied by all this. And you spotted this very important point. This does not mean a lot. Having something so small in double precision computation doesn't mean a lot. So this is it is well known that that sometimes in those methods you have really quantities that go to zero and they go below machine precision. There are quantities like this. Of course, they are not really meaningful. It means that it is small, but I don't consider this as something which really makes sense to 10 to minus 30 in finite precision, in double precision. No, it doesn't. But this is what I conclude from that is that my gap is good. So this is satisfactory. So, and this is for a continuous accuracy level. So it means that my bounds ask for perturbation of the matrix, which is something, and I exactly provide a matrix with this norm to my algorithm. Multiprecision is a discrete case, and in the discrete case, you get similar plots. Okay. So, and this is maybe the most interesting one. So what you see is that, so this is the value of my quadratic. And here you see the perturbation that have been actually implemented in the algorithm. And what you see is that in this algorithm, you start, or your bounds, they need very accurate matrix vector product at the beginning, but then you relax quite a lot your norm. And at the end, this is the value, the relative error E, measured in norm A-AMS1, and you see here that the value of the perturbation is very high. And this would correspond maybe to 1 or 2 digits of accuracy. It's a very, very coarse approximation. And this is a surprise, of course, because with an intuition on maybe the one that we have on first order method, you think that if at a certain point the error you do on the gradient is very large, then you jump to a point which is meaningless, and then maybe you have to pay a lot to come back to the... And here, what happens is that, so our understanding of this is that contrary to first order method, even if your recurrence are short, you keep some memory of, it's a method with memory, because at the current step, even if you do very little computation, in fact, you find a point that minimizes over all the Kreyler subspace. And so this is why, I mean, qualitatively, the algorithms are very different. So if you want to get this now for first order method, maybe you need something like, something which is implemented in some of the framework is a BFGS method for, so it's an option in PyTorch, for instance, you can use BFGS. And this is something that enables you to have an algorithm with this particular robustness. So this, for us, this was really interesting because it means that you can really save a lot in the computations. Okay, so just a quick point, which is not so important for us, is that in the control of the perturbation, I had norms like this with A-1, and so on. You may say that, oh, you want to avoid using A-1, even using A, and you have a control which is based on A-1. It is a bit strange. So first comment is that you don't need the same accuracy on this A-1 as the one you need for the solution of your linear system, because this is just a scalar which is used to control your system. So maybe you need 1 bit of accuracy on this one. So computing this with one digit of accuracy, just the order of magnitude of this is much easier than solving a linear system first. And another alternative would be to find proxies for all these quantities, which is what we did, and similar things happen. Okay. It's quite interesting to see also that these algorithms that are similar, that are the same on the paper, they perform differently in our schemes. Okay, so I have still a few minutes to say a few words about what we did for the more general setting, which is now minimizing a general function, non-convex function. Probably I will just present the algorithm and give you the final results. So now I want to minimize a function. So it could be your neural network if you like. So it is non-convex. And I assume, again, that I have access to a noisy quantity with a noise I can control. Here it's the noise on the function value, which I can control, and also a norm on the gradient, which I can control. Okay, so this is just, so we take a relative error for the gradient, absolute for the function, and with this we can prove something. So similar to what we got with the gap, you obtain convergence of your algorithm if these two quantities, if the sum of these two quantities is below epsilon, and this is the case if this quantity is less than epsilon divided by 1 plus kappa g, where kappa g is any positive constant, provided that the perturbation of your gradient is also less than kappa g. So this is just triangular equality. So if you sum this, you use the bound here, and you sum this plus this, and less than epsilon, and you get that this has to be less than that. So this would be, again, our stopping criterion. Okay. So what is a trust region algorithm, which I'm going to use? So it's an algorithm which I divided into 2 parts here. So my non-convex function, I'm going to make an approximation, a quadratic approximation of this function. Important thing to notice is that hk need not be the true Hessian. It could be an approximation that you get. Okay, so what you do in this algorithm, you minimize this quadratic model within some region. And you will control in the algorithm the value of delta k. So why do you do that? It's because gk at least, even if it's a noisy quantity here, it's a very local information for your function, it's just a gradient. So this quadratic is a good approximation of your function only within some region that is controlled here by this radius of the trust region. So you approximately minimize your quadratic model within the trust region. By approximately minimize, I mean that I need a decrease of my quadratic function, which is bounded by this. So this looks quite complicated, but it is something that you would obtain just by minimizing the quadratic in the direction of the negative gradient of this quadratic. So this is, obtaining this just cost one matrix vector product with the Hessian. So this is a very easy. And
I'm not familiar with that. So how do you choose H?
So H, first it can be 0 if you like. And then you recover a first order method, and then you would control the so-called learning rate with this guy. But otherwise, what you want to have an approximation of your quadratic function, which is as good as possible. So you can, for instance, adaptively during your algorithm, you can compute this approximation of hk. How do you do that? It's an area of quasi-Newton method, where you are at the current point, you have an approximation hk of your matrix, And you consider this relation. This is called a second equation. So this equation would be satisfied not with the true Hessian, but with an average Hessian. So in fact, what you have if you take the average of your Hessian like this, so if you compute this quantity just by fundamental calculus theorem, you get this. So you said that so the claim is that not the true Hessian would satisfy this, but an average Hessian over your current step would satisfy this. So you are looking for an approximation of your function that uses this kind of information. And you do this in the least norm sense. So you look for the least perturbation, so delta H, in some norm. It's particular norm, such that H plus delta H times, and this is called SK, is equal, and this is called YK. So using the newest value of your iterate and newest value of your gradient, you consider a relation that would hold with the average Hessian, and you put this as a constraint for the computation of a perturbation of your current approximation. And this is
looks like a minimizing problem. That's the one you're starting from.
But this one is now purely quadratic. This is just, it depends on the norm, but if you take, for instance, the Frobenius norm, this is a quadratic problem with a linear constraint. So you have an explicit formula for all this. And what is very important is that the updates are, in all this approach, they are low rank updates. So it's very cheap to compute this. So in a trust version method, I minimize approximately this quadratic model. And then what do I need to do? This is very different from first order method. I may reject my step. So this is crucial. So I will compute a quantity which is the decrease of my nonlinear function divided by the decrease of the quadratic model. I will compare the decrease I obtain with my model and my function, and if this is high enough, I would say that my model is good, and I will accept my step. So this is the condition. There is here a quantity which is taken 10 to minus something. We don't care about this constant, so this does not depend on the iteration. So if the ratio is higher than some quantity, I accept my step. Otherwise, I will refuse my step. I will stay at the same point because my step is very bad from the point of view of the minimization. So I don't want to go in a place which is badly predicted because my model is not good enough. First thing. And second thing is I need to update also my trust region radius. And again, based on the same principle, if my ratio is very high, I will increase my trust region. Why? Because my model was good, and maybe I will be optimistic, and I want to make a bigger step. And what is interesting with this algorithm is that it learns automatically how to choose what we call the learning rate in a method. So if you forget about playing with inexact quantities, this algorithm is converging whatever the starting point to a critical point. So there are very mild conditions, and so this is very robust, and it converges whatever the starting point.
converge in very large time?
People are a bit skeptical first, even if I'm in this business. So the number of iterations to reach gradient less than epsilon is 1 over epsilon square. So, okay, it is not very good because you have a number of iterations. So this is 1 iteration, and the number of iterations would be that. So it's pretty high. And in fact, you get the same behavior, whatever, the same bound, whatever you choose for H, whether it is 0, whether it's a pure quadratic model, and so on. So this means that maybe this bound is very pessimistic, but in this business, it is the only bound that we have. It's you want to drive a gradient of f of x less than epsilon. So it's
near critical.
Yeah, near critical. Okay, so maybe I have. So I will just present you briefly what we can do. So I think it was very important for this committee to talk about second order method, because of course, if you take a pure true Hessian, this is very expensive. But there are many things that you can do. You can do this quasi-Newton update of the Hessian, or you can also compute the Hessian on your pure batch. Maybe work with how to represent.
Can this be used to escape mediocrity in my problem?
It's what we discussed yesterday.
Sometimes compute a little bit of the true Hessian.
Yes. So this is why I think it's an important tool, but people are a bit scared when we talk about Hessian, because Hessian, the dimension of the Hessian is the number of weights that you have on your neural network. But another point is that you have also matrix-free variant of all these methods, and getting the matrix vector product with the Hessian. This is available. There are some tricks to do it with automatic differentiation. So in this setting, we can prove also that we can prove the convergence of this algorithm. So here, the important point is how you choose the error, and the error here, So this is the bound that is on the function. So the error has to be less than a quantity which not has to. It's of course it's just a sufficient condition. We can prove convergence provided that the error you do on your function is bounded by the decrease of the model multiplied by epsilon 0. And why this for the function and for the gradient you have also a control of WG here, and why are those quantities important? Is if you consider the analysis of the method, you are playing with this row, with this ratio, and if you introduce the inexact quantities here, you can easily bound your ratio, okay, provided that this error is proportional to the denominator here. So it's a way to prove the convergence even with inexact quantities. This is a proof, and then you can do computations, and I will stop after that. So this is if you do something stupid, you take your double precision algorithm and you run it in single precision, and you get S here. H is half precision. What happens here is that the number of problems you can solve is dropping. So here you can solve 82 problems in a collection of 100. And if you use only half precision and don't change at all your algorithm, you lose a lot of robustness due to this rounding error. And if you implement the schemes that we propose, then with the inexact scheme, you see, so we propose our algorithm leaves some freedom in the way that we choose a constant in front of this reduction of the quadratic, and depending on the option you choose, you have different algorithm. So you see that you have if epsilon is not too small, you have a reasonable robustness of our method. And what is really important is a reduction in the costs that you see. So one would be the cost of the original method. And here you see that by our approximate method, we managed to reduce the cost of the function and gradient evaluation. And then just conclusion is, I think it's very important to consider running our algorithm in inexact precision, and also tuning, being able to tune our precision to get good results. Thank you very much.